Assalamu alaikum students. I am Wasim Ikram. This is the 8th lecture in a series of 45 lectures on digital logic design. कैसे हैं आप? इंशाल्लाह अच्छे होंगे। पिछली दफ़ा हमने ऑपरेशनल कैरेक्टरिस्टिक्स पे बात शुरू की थी। मुश्किल टॉपिक था पर काफ़ी डिटेल में डिस्कशन हुई थी एंड आई होप यू हैव अंडरस्टूड द टॉपिक। आज हम इंशाल्लाह एक नए टॉपिक पे बात शुरू करेंगे, बूलियन अलजेब्रा। But before we start with Boolean algebra, let us quickly revise the things which we had done in the last lecture. In fact, एक मैंने table दिखाना था जिसमें we compare different CMOS and TTL gates and we look at the actual values. So let us start our discussion by revising the contents which we had studied in the last lecture. ऑपरेशनल कैरेक्टरिस्टिक्स थे, 4-5 इम्पॉर्टेंट पैरामीटर्स थे। पहला पैरामीटर था डीसी सप्लाई वोल्टेज। सो हर सर्किट को एक डीसी सप्लाई वोल्टेज चाहिए ताकि वो काम करे। सो 5 वोल्ट्स यूजुअली हम यूज़ करते हैं, तो टीटीएल के लिए 5 वोल्ट सप्लाई वोल्टेज चाहिए। इसी तरह सीमॉस के लिए भी 5 वोल्ट्स चाहिए। सीमॉस की एक और सीरीज़ है जिसमें 3.3 वोल्ट्स सप्लाई वोल्टेज चाहिए। Then we talked about the noise margin. Noise margin ये था कि हर logic level high या low it is represented by certain voltage levels. So अगर वो signal जो है it is within those voltage levels तो फिर तो सारा circuit ठीक काम करेगा. But due to some external noise, some other factors, जो logic 1 या logic 0 की representation है वो उस voltage range से बाहर आ जाती है उसमें. Due to that, the circuit might not work. So हमने वो noise margins calculate किए थे। उसमें हमने ये देखा था कि जो CMOS का 5 वोल्ट वर्जन है उसके noise margins ज़्यादा हैं। That means वो एक noisy environment में बड़ी अच्छी तरह काम कर सकता है। The third parameter which we looked at was the power dissipation. हर circuit को power use करता है, of course current flow होती है उसमें, energy चाहिए उसको। वो कितने वॉट्स कंज्यूम कर रहा है उसमें। सो हमने टीटीएल के लिए देखा, सीमॉस के लिए देखा। टीटीएल के लिए जो पावर रिक्वायरमेंट है वो मोर लेस फिक्स्ड है। सीमॉस के लिए जो पावर रिक्वायरमेंट है वो वेरी करती है विद रिस्पेक्ट टू फ्रीक्वेंसी, क्योंकि सीमॉस सर्किट्स में कैपेसिटिव लोड है। जब कैपेसिटर होगा तो वो चार्ज भी होगा, डिस्चार्ज भी होगा। वो चार्ज डिस्चार्ज किस रेट पे होगा वो डिपेंड करता है किस फ्रीक्वेंसी पे वो ऑपरेट कर रहा है। So when the frequency of a CMOS circuit increases, the power dissipation also increases. तो उसका CMOS circuits का variable power dissipation होगी। इसको जब हम measure करते हैं या कहीं आप लिखते हैं तो एक static power dissipation होगी और एक dynamic power dissipation होगी। वो अभी आगे जाके हम टेबल में देखते हैं। एक और जो पैरामीटर हमने देखा था प्रोपेगेशन डिले का। प्रोपेगेशन डिले हमने ये कहा था कि हर गेट जो है अगर उसके इनपुट पे कोई आप वेरिएबल्स अप्लाई करें, ज़ीरोज़ एंड वंस, तो एक ख़ास डिले के बाद उसके आउटपुट पे कोई वैल्यू आपको मिलेगी। सो ये जो डिले है दैट वुड बेसिकली डिटरमिन हाउ फास्ट ए सिग्नल कैन चेंज एट द इनपुट ऑफ एनी गेट। डिले फैक्टर से अगर ज़्यादा हाई फ्रीक्वेंसी पे चेंज हो रहा है तो वो काम नहीं करेगा उसमें। एक हमने बात की थी प्रोडक्ट ऑफ द स्पीड एंड डिसिपेशन। इन दोनों का प्रोडक्ट एक नंबर देगा, उससे आप कंपेयर कर सकते हैं डिफरेंट गेट्स। फाइनली हमने देखा था फैन आउट। फैन आउट ये था कि हाउ मेनी गेट्स कैन वी कनेक्ट टू द आउटपुट ऑफ अनदर गेट। Well, basically we said it depends on the current which the gate can supply to the inputs of different gates. Again restriction है, TTL में fixed number of fan outs हैं, CMOS में ये depend करता है frequency पे। अगर आप हाई फ्रीक्वेंसी पे सर्किट ऑपरेट करना चाह रहे हैं देन आपका फैन आउट कम होगा। दैट मीन्स कम नंबर ऑफ गेट्स कनेक्ट करने पड़ेंगे। अगर आप लो फ्रीक्वेंसी पे ऑपरेट कर रहे हैं देन यू कैन कनेक्ट मोर नंबर ऑफ गेट्स टू द आउटपुट ऑफ ए गेट। सो ये 5 इंपॉर्टेंट पैरामीटर्स थे। लेट अस हैव ए लुक एट द टेबल जहां हम डिफरेंट गेट्स को कंपेयर करते हैं और एक्चुअल जो नंबर्स हैं उनको ज़रा देखते हैं उसमें। उसके बाद इंशाल्लाह हम स्टार्ट करेंगे बूलियन अलजेब्रा पे। लेट अस फर्स्ट कंसिडर द TTL सीरीज ऑफ गेट्स। वी हैव द 74 स्टैंडर्ड गेट, द 74S Schottky gate, the 74LS the low power Schottky, 74AS the advanced Schottky, and the 74ALS, the advanced low power Schottky, and the 74F, the fast version of TTL. इनके अगर propagation delays को देखें, the standard version has a propagation delay of 9 nanoseconds, which is almost the highest propagation delay. 74LS का propagation delay 9.5 nanoseconds है. Fast का और ALS का बहुत कम है, AS का भी बहुत कम है, 1.7 है. पावर डिसिपेशन को अगर देखें, मिली वॉट्स में मेजर करते हैं, 74S शॉटकी की पावर डिसिपेशन सबसे ज़्यादा है, 20 है. लो पावर शॉटकी की पावर डिसिपेशन 2 है. इसी तरह एडवांस्ड लो पावर शॉटकी की पावर डिसिपेशन 1.2 है. एक इम्पॉर्टेंट जो पैरामीटर था, स्पीड पावर प्रोडक्ट, पिको जाउल्स में मेजर करते हैं. सो इनको ज़रा अगर देखें आप, 4.8 जो है वो लोएस्ट है ALS का, राइट. सो ये जो गेट है सारों से बेहतर है इन टर्म्स ऑफ पावर डिसिपेशन एंड प्रोपेगेशन डिले. जो स्टैंडर्ड वर्जन है उसका हाईएस्ट है, 90 है. मैक्सिमम क्लॉक रेट जिस पे ये ऑपरेट कर सकते हैं वो भी इधर दिया हुआ है. सो स्टैंडर्ड जो TTL है गेट 35 मेगाहर्ट्ज पे ऑपरेट कर रहा है. जो एडवांस शॉट की है वो 200 मेगाहर्ट्ज तक ऑपरेट कर लेता है. एडवांस लो पावर शॉट की तकरीबन 70 मेगाहर्ट्ज तक ऑपरेट कर लेता है. फैन आउट जो है अगेन 74 स्टैंडर्ड जो है 10 गेट्स कैन बी कनेक्टेड. इसी तरह जो शॉट की है 20 गेट्स कैन बी कनेक्टेड. एडवांस शॉट की के साथ 40 गेट्स तक आप कनेक्ट कर सकते हैं. लेट अस नाउ लुक एट द CMOS सीरीज. पहले हम 5 वोल्ट सीरीज को देखते हैं, उसके बाद 3.3 वोल्ट सीरीज को देखते हैं. So 5 volt series में you had the 74HC, 74AC and the 74AHC. Propagation अगर delays देखें ये कम हैं as compared to TTL logic के. Power dissipation तो बहुत ही कम है, 0.00275 है for 74HC, इसी तरह 0.0055 है for 74AC. CMOS सीरीज में हमने ये बताया था कि पावर डिसिपेशन वेरी करती है लो फ्रीक्वेंसी पे एंड हाई फ्रीक्वेंसी पे. सो स्टैटिक पावर डिसिपेशन, स्टैटिक जो है दैट मींस नो ऑपरेशंस और लो फ्रीक्वेंसीज, उस पे पावर डिसिपेशन एज आई सेड बिफोर इट्स 0.00275. सेम गेट अगर 100 किलो हर्ट्ज पे ऑपरेट कर रहा हो तो उसकी पावर डिसिपेशन इंक्रीज हो जाती है टू 0.0625. सिमिलरली फॉर 74AC द पावर डिसिपेशन इंक्रीजेस टू 0.08 एट 100 किलो हर्ट्ज. स्पीड पावर प्रोडक्ट जो है एट 100 किलो हर्ट्ज वो 1.125 है 74HC के लिए, 0.4 है 74AC के लिए एंड 0.23 है 74AHC के लिए. अगर स्पीड पावर प्रोडक्ट कंपेयर करें TTL के साथ तो अगेन बहुत कम है. मैक्सिमम क्लॉक रेट it is 50 for HC, for AC it's 160 megahertz and for AHC it's 170 megahertz. Now let us have a look at the 3.3 volt CMOS series, the 74LV, the 74LVC and the 74ALVC. Propagation delay again are very low, 9, 4.3 and 3 respectively. Power dissipation, the static power dissipation is again very low, 0.0016, 0.0008 and 0.0008 for the 3 gates respectively. Operational clock rate, maximum clock rate जो है megahertz में it's 90, 100 and 150 respectively. We have just looked at some parameters of TTL and CMOS gates. So by comparing those numbers, you can just see which gate is better and which particular gate is required for your particular implementation. Now let us start with today's topic, Boolean algebra. Boolean algebra, how is it different from the conventional algebra? Well, Boolean algebra has 2 values. Conventional algebra में बहुत सारी values आती हैं. Boolean algebra में since it is dealing with binary values, so उसकी एक value 0 होगी, दूसरी value 1 होगी. So let us start by looking at some definitions of Boolean algebra. Boolean algebra में हम literal use करते हैं, complement की बात करते हैं and variables की बात करते हैं. What is a variable? Variable programming में भी आप use करते हैं. It is a symbol which represents a value. So Boolean algebra में a variable is usually a capital letter, alphabet letter A, B, C, Z, N, right? So it represents a value. Value क्या होगी? Either it's going to be a 0 or a 1 because it is of course representing a Boolean value or a binary value. Complement क्या है? Complement हमने ये बताया था the inverse of a variable. So if variable A has the value 0, A bar would have the value 1. So the bar represents the inverse of the complement. Literal क्या है? Literal could be the variable or its complement. So let's say B bar है, it is considered to be a literal. B जो है उसका complement, again it is considered to be a literal. So ये तीन definitions हैं जो हम बार बार use करने होंगे. Okay, Boolean algebra क्यों कर रहे हैं? Basically mathematics हम क्यों use कर रहे हैं? एक फ़ायदा तो मैथमेटिक्स का ये है कि all real world problems can be represented in the form of equations. फ़ायदा क्या होता है? उससे हम बहुत सारे रियल वर्ल्ड फिनोमेनल्स चेक कर सकते हैं या इम्प्लीमेंट कर सकते हैं इन द फॉर्म ऑफ मैथमेटिकल इक्वेशंस. लेट मी गिव यू एन एग्जांपल. एक आप आयरन रॉड लें, लेट्स से 1 इंच डायमीटर का. एक एंड पे आप उसको हीट करना शुरू करें एंड यू नीड टू डिटरमिन कि दूसरे एंड पे लेट्स से 1 फुट का लॉन्ग रॉड है, दूसरे एंड पे कितने टाइम में 50 डिग्रीज टेम्परेचर हो जाएगा. Right? Now this entire heating of an iron rod can be modeled using a mathematical equation. Now if you have an equation, then you don't need to perform an experiment. You don't need to get an actual rod and heat that. ठीक है? आप एक equation से ही आप different values डालें और आप एक answer calculate कर सकते हैं. In fact, if you have an equation, then you can use different rods. Different metal के rods हो सकते हैं, different diameter के rods हो सकते हैं, right? So mathematics solves the problem. आपको practically कोई चीज़ करनी नहीं पड़ेगी. Similarly, Boolean algebra allows you to represent digital circuits in terms of expressions. फ़ायदा क्या होगा? एक फ़ायदा तो ये है कि let's suppose you have a very complex, complicated circuit having different gates. अब वो सर्किट कैसे परफॉर्म करेगा, क्या आउटपुट आएगी? वेल, वन वे इज़ टू प्रैक्टिकली इम्प्लीमेंट दैट सर्किट. आपको टाइम ज़्यादा लगेगा, आपके पैसे खर्च होंगे उसमें. सो द ईजीएस्ट वे वुड बी टू रिप्रेजेंट दैट सर्किट थ्रू ए बूलियन एक्सप्रेशन, ए मैथमेटिकल एक्सप्रेशन. आप डिफरेंट इनपुट कॉम्बिनेशन उसमें आप अप्लाई करें एंड यू गेट द आंसर. सो यू कैन ईजिली चेक इफ दैट पर्टिकुलर सर्किट इज गोइंग टू वर्क करेक्टली और अदरवाइज. You can use a Boolean expression to simplify circuits. Let's suppose you have a circuit composed of 20 gates. It performs a certain function. Now, you could implement the same function using 5 gates. Now, if you implement a circuit having 5 gates, that means the circuit is going to be faster, less propagation delay, the power requirement would be reduced, so it would be better than the previous circuit which uses more gates. Now, how would you simplify a circuit? Well, by looking at the circuits, it's very difficult to find out the simplified version of that circuit. A better way would be to write an expression of that original circuit and then using the rules and laws of Boolean algebra simplify the expression. You would get a simplified version of the expression, and if you directly implement the circuit using that expression, you would have a simple circuit. So let us look at Boolean operations. शुरू में हमने बात की थी 2 Boolean operations हैं जो important हैं और throughout Boolean logic में use होते हैं. Boolean addition and Boolean multiplication. Boolean addition is performed by an OR gate. So 2 इनपुट का OR gate है A plus B. ये A plus B जो है this is known as a sum term because sum कर रहे हैं ना, addition कर रहे हैं. Boolean multiplication is performed by an AND gate. So if you have a 2 input AND gate, you have a product term A dot B. A dot B is known as the product term क्योंकि multiply का result है, multiplication का result है. Let us look at some other sum terms and product terms, and let us look at what would be the output of this sum term if one of the variables is set to 0 or 1. Let us first look at Boolean addition. Boolean addition gives us a sum term. A sum term is described as sum of literals. So as you can see, A plus B is a sum term, which is in fact a sum of literals. Another term, A plus B bar, again it's a valid sum term. It is again a sum of literals. The third expression, A bar plus B bar plus C, is again a sum term composed of 3 literals. Now a sum term is equal to 1 if any literal is equal to 1. Considering A plus B, A 1 हो जाए या B 1 हो जाए, the output is going to be a 1. Similarly, A plus B bar को अगर देखा जाए, इनमें से कोई भी literal अगर 1 हो जाए, output 1 होगी. A sum term is equal to 0 if all literals are equal to 0. So considering A bar plus B bar plus C, the output or the sum term is 0 if A bar is 0, B bar is 0 and C is 0. Similarly, considering the term A plus B bar, the output is 0 or the sum term is 0 if A is 0 and B bar is 0. Let us now look at Boolean multiplication. Boolean multiplication results in a product term. Product term is described as a product of literals. So you have 3 product terms as can be seen: AB, AB bar and A bar, B bar, C. Now a product term is equal to 1 if all literals are equal to 1. So A, B would give you a 1 result if A is 1 and B is 1. Similarly, A, B bar would give you a 1 result if A is 1 and B bar is 1. A product term is equal to 0 if any one literal is equal to 0. So considering the product term A bar, B bar, C, if any one literal is 0, the entire term would be 0. So if A bar is 0 or B bar is 0 or C is 0 or all 3 terms literals are zeros, the product would be a 0. We've just looked at Boolean addition and Boolean multiplication. We have looked at the sum term and the product term. Now when you write Boolean expressions and solve Boolean expressions, they are solved on the basis of certain rules, laws and theorems. Normal algebra में भी कोई भी आप equation को solve करते हैं तो it is done according to certain rules and theorems. So now let us look at some rules and laws and theorems being applied in Boolean algebra. There are 3 laws being applied in Boolean algebra: the associative law, the distributive law and the commutative law. ये तीनों लॉज जो हैं नॉर्मल अलजेब्रा में भी यूज हो रहे हैं और उसी तरह बिल्कुल यूज होते हैं. Then there are certain rules. I think there are about 12 rules. Again, we are going to be looking at those rules. Then we have 2 theorems, De Morgan's theorems. So again, we would be looking at the 2 theorems. So now let us have a look at the 3 laws, the rules and the theorems applied in Boolean algebra. The basic laws of Boolean algebra are the same as ordinary algebra and hold true for any number of variables. So let us start by looking at the commutative law. Commutative law for addition states that sum of A literal and B literal, that is A or B, is equal to B or A. If you have 3 literals A, B and C, the commutative law states that A or B or C is equal to C or B or A. Implementation wise, an OR gate is used. So if you have a 2 input OR gate, it does not matter if you connect the literal A to the first input or to the second input. In both cases, the output would be the same. Let us consider the commutative law for multiplication. The commutative law for multiplication states that product of literal A and B is equal to product of B and A. Again, implementation wise, an AND gate is used because multiplication of course is done using AND gates. So according to the commutative law for multiplication, it does not matter if you connect the literal A to the first input or the second input of the AND gate. The result would always be the same. Again, you could have multiple literals A, B, C and D. the law holds true for multiple literals. Let us now consider the associative law for addition. The associative law for addition states that sum of B and C literals, that is B or C odd with A, is the same as A or B odd with C. Implementation wise, you require a combination of two OR gates. So the inputs are 3, A, B and C. So any of these three inputs can be connected to any of the three literals A, B or C. The output would be the same. Let us consider the associative law for multiplication. The associative law for multiplication states that the product of B and C ANDed with literal A is the same as the product of literals AB ANDed with C. Implementation wise, you would use a combination of two AND gates. So altogether you would have three inputs. Any of the three literals A, B and C can be connected to any three inputs. The output would be the same. You could have 4 literals, 5 literals. The associative law for multiplication would hold true. The distributive law states that B or C ANDed with A is equal to A, B odd with A, C. The left side of the expression, that is B or C ANDed with A, can be implemented by using a combination of AND gate and OR gate. The inputs B and C are odd together. The output of the OR gate is connected to an AND gate and the result is B or C ANDed with A. The right side of the expression, A, B, the product of A, B odd with the product of A and C, can be implemented using 3 gates, 2 AND gates and an OR gate. So the first AND gate is connected to inputs A and B. The product is AB. The second AND gate is connected to inputs A and C. The product is AC. The outputs of the 2 AND gates are connected to an OR gate. The output of the OR gate is product AB odd with product AC. Let us have a look at 12 rules of Boolean algebra. The first rule, A or 0 is equal to A. This can be proved by assigning values to the variable A. If A is 0, what is the result? The result is 0. If A is 1, what is the result? The result is 1. So the output is the same, is equal to A. The second rule, A or 1 is equal to 1. Now by assigning values to the variable A, 0 or 1, the output remains a 1. The third rule, A product 0. So as we have discussed before, anything multiplied by 0 gives you a 0. So A product 0 is equal to 0. The fourth rule, A product 1 is equal to A. We have studied this before as well. Anything multiplied by 1 gives you the same thing. Rule number 5, A or A is equal to A. Again, this can be proved by applying or assigning values to the variable A. So if A is 0, so it's 0 or 0, which is equal to 0. If A is 1, then the rule becomes 1 or 1, the result is 1. Rule number 6, A or A bar is equal to 1. Again, let's apply the two values to the variable A. If A is 0, then the equation becomes 0 or 1, the result is 1. If A is 1, the equation becomes 1 or 0, the result is again a 1. Rule number 7, A product A is equal to A. Again, let's check. If A has the value 0, so the equation becomes 0 and 0, the result is 0. If A is equal to 1, it's 1 and 1, the result is 1. Rule number 8, A and A bar, the result is 0. Applying the two values, if A is equal to 0, the equation becomes 0 and 1, the result is 0. Similarly, if A is equal to 1, the equation becomes 1 and 0, the result is again a 0. Rule number 9, A double bar is equal to A. Double bar means complemented twice. So, if you have a single bar, that means complemented once. If you have a double bar, you complement the complement again. So, that means you have just cancelled out the two complements. So, if A is equal to 0, the answer would remain a 0. If A is equal to 1, the answer would remain a 1. Rule number 10, A odd with the product term AB, the result is A. We can prove this. A is common in both the terms. So, if you take A as a common, you are left with 1 or B. Now, 1 or B, if you apply rule 2, is equal to 1. So, you are left with A product 1, which is equal to A. Rule 11, A or A bar B, which is equal to A or B. This can again be proved. A can be multiplied with sum of B plus 1. The result is 1. So, you multiply A with 1, it would remain an A. So, you multiply A with B or 1, you simplify the equation, this gives you AB plus A and the previous term A bar B. Now, readjusting the expression, you have A plus AB plus A bar B. Now, considering B, which is common in terms AB and A bar B, if you simplify this, the equation turns out to be A plus B. The last rule, rule number 12, A or B ANDed with the sum term A plus C or A or C. The result is A odd with the product term B C. This can be proved by rewriting the equation. So, A multiplied by A gives you A. A ANDed with C gives you AC. B ANDed with A gives you AB. B ANDed with C gives you BC. Now, considering the first three terms A, AC and AB, you have a common A. So, if you remove the common A, the remaining portion is equal to 1. So, the equation simplifies to A plus BC. Now, let us consider De Morgan's theorems. There are two theorems. The first theorem states the complement of a product of variables is equal to the sum of the complements of the variables. In form of an equation, AB whole bar is equal to A bar plus B bar. De Morgan's theorem, the first theorem, holds true for any number of variables. Implementation wise, AB whole bar is implemented using a NAND gate. The right side of the equation, A bar plus B bar, is implemented again by a NAND gate, but the alternate symbol of the NAND gate is used. Let us consider the second theorem. De Morgan's second theorem states that the complement of sum of variables is equal to the product of the complements of the variables. Writing the expression, it is A or B whole bar equals to A bar ANDed with B bar. Implementation wise, you have a NOR gate. So, A NOR B gives you A plus B or A or B complemented. The right side of the equation, A bar ANDed with B bar, can be implemented using the same NOR gate, but represented in its alternate symbolic form. Again, the second theorem of De Morgan's holds true for multiple variables. De Morgan's theorem can be applied to expressions having any number of variables. So let us have a look. The first expression, x and y and z whole bar is equal to x bar plus y bar plus z bar. Similarly, x or y or z whole bar is equal to x bar ANDed with y bar ANDed with z bar. De Morgan's theorem can be applied to a combination of other variables. Let's have a look at the expression. The expression is a or bc. This is considered to be a single term ANDed with another term which is ac ORed with b. Both these terms are complemented. So you have an entire bar over the product of the two terms. These two terms, according to De Morgan's theorem, can be written as a plus bc whole bar plus ac plus b whole bar. The plus of course indicates the OR operation. This equation can be further simplified to a bar bc bar plus ac bar b bar. This can further be simplified to a bar ANDed with b bar plus c bar plus b bar ANDed with sum of a bar and c bar. This expression can be further rewritten as a bar b bar ORed with a bar c bar ORed with a bar b bar ORed with b bar c bar. Final expression is a bar b bar plus a bar c bar plus b bar c bar. We have looked at the laws, rules and theorems used in Boolean algebra. You need to practice these laws, rules and theorems. You need to know about them because we would be applying these rules and laws throughout this course. Let us now look at the application of these Boolean expressions to analyze a circuit. Let us consider an expression a plus b ANDed with c. Now, what kind of information does this expression convey? Well, a ORed or b means a two input OR gate is being used. The output of this is connected to an AND gate and the other input of the AND gate is connected to the variable c. So basically a or b ANDed with c gives you three variables, right? So if you write out the function of this OR gate and AND gate circuit, कितने inputs होंगे, कितने columns होंगे, 3 columns होंगे, कितनी possible input combinations हो सकती हैं? Well, since there are 3 input variables, therefore you have 8 possible combinations. What is the output of this circuit? Again, you can analyze that by applying the appropriate inputs. Let's say you start with the combination 0, 0 and 0. So A or B is 0 or 0, which is 0. ANDed with C, anything ANDed with 0 is going to give you a 0. So the output is going to be 0. Instead of you using all the 8 terms, you can find the output just by looking at the equation. C is ANDed with the OR of A and B. A or B ANDed with C. Now, if A or B is a 1 and C is a 1, then you would get a 1 output. If either A or B is a 0 or C is a 0, you would get a 0 output. Right? So, if we know this, then we can easily determine for which particular combination of zeros and ones you would get a 1 output. Let us have a look at another circuit and let's analyze that circuit using the Boolean expression. Let us consider the expression A and B ORed with C bar and the entire term ANDed with D. Now, what type of or what kind of information does this expression convey? basically there are 4 variables. So the circuit represented by this expression is going to have 4 inputs and of course a single output. Now by looking at the expression again, the variables A and B are ANDed together. So a 2 input AND gate is required. The output of the AND gate is ORed with C bar. That means a NOT gate is required. The input of this NOT gate is connected to C. The output of the NOT gate is C bar. So the output of the NOT gate and the output of the AND gate are connected to the input of an OR gate. So it's a 2 input OR gate. The output of the OR gate would of course be A and B ORed with C bar. We have the 4th variable, variable D. It is ANDed with the term AB plus C bar. So how do we AND D with the AB plus C bar term? You use an AND gate, a 2 input AND gate. Now for which particular combinations of ones and zeros for the inputs A, B, C and D, the output is going to be a 1. Let us again have a look at the expression. The output is going to be 1 if D is 1 and the term A, B plus C bar is a 1. Now how would the term A, B plus C bar be a 1? If A, B is a 1 and the literal C bar is a 1. How is the AND term A, B going to be 1? If both A and B are 1s. The literal C bar, how is that going to be 1? If C is 0. So when do you obtain a 1 output? When A is 1, B is 1, C is 0 and D is 1. So for this particular combination of ones and zeros, you obtain a 1 output. Now this can be verified by drawing out a function table. So what is the size of the function table? How many input columns are required? Basically there are 4 variables A, B, C and D. So there are 4 input columns A, B, C and D. How many input combinations are possible? Since there are 4 variables, so 16 different input combinations are possible. The output of course is 1 represented by F. Now let us write all the outputs for each of these 16 combinations. Starting with the first combination of 0, 0, 0, 0, the output is 0. Why? Because D is 0. Considering the second input 0, 0, 0, 1. Now in this particular case D is 1 and C is 0. So both the conditions are satisfied. The answer is, or the output is 1. Similarly for the input condition 0, 1, 0, 1. Again D is 1 and C is 0. The conditions are satisfied. The output is again going to be a 1. Let us consider the input 1, 0, 0, 1. Again D is 1, C is 0. The conditions are satisfied. The output is again going to be a 1. Let us consider inputs. The inputs 1, 1, 0, 1. In this particular case D is 1, C is 0, A and B are both 1s. So all 4 conditions are satisfied. The output is going to be a 1. The last input combination 1, 1, 1, 1. D is a 1, C is a 1. So this particular condition is not satisfied, but A and B both are 1s. Therefore the output is again going to be a 1. We have looked at 2 examples of analyzing Boolean circuits or logic circuits using Boolean expressions. Basically we would be using this method to analyze different circuits throughout the course. So it is important that you learn to use these expressions to analyze circuits. इसका तरीका क्या है? I would suggest you just write any expression, simple expression of 3 or 4 variables, then try to decipher that expression. उससे आप एक circuit implement करके देखें उसमें कौन से gates हैं और क्या बन रहा है उसमें. Then I would suggest that you look at the expression and see what, for which particular combination of inputs you get a 1 output. okay? इसको आप वेरीफाई कर सकते हैं अगर आप उसका फंक्शन टेबल बना लें. सो अगर आपकी एक्सप्रेशन में लेट्स से 4 वेरिएबल्स हैं तो आपका फंक्शन टेबल जो है उसमें भी 4 कॉलम्स आएंगे, उसमें 16 कॉम्बिनेशंस होंगी, तो सारी 16 कॉम्बिनेशंस लिख लें उसमें और उसके साथ आप आउटपुट कैलकुलेट करते जाएं यूजिंग दी सर्किट, और उसको आप वेरीफाई कर दें बाय अप्लाइंग दोज वैल्यूज़ इन द एक्सप्रेशन, और एक्सप्रेशन का आउटपुट भी देख लें तो दोनों चीज़ें एक दूसरे को वेरीफाई करेंगे. सो इट इज़ इम्पॉर्टेंट दैट यू प्रैक्टिस विद द एनालिसिस ऑफ सर्किट्स यूजिंग दीज बूलियन एक्सप्रेशंस. Now, the other thing which we said we use the expression is to simplify circuits. अगर सर्किट कोई एक बना हुआ है उसको सिंप्लीफाई करना देखने से आपको अंदाज़ा नहीं होगा. So the best way is to write an expression representing that circuit and then apply the rules of Boolean algebra, laws and theorems जो हमने discuss किए थे. That would give you a simpler expression. When you have that simple expression, then of course you can always implement a circuit using that expression. The expression which we are going to use and simplify in the example is a 3-variable expression. It represents a large circuit. We are going to be simplifying this expression using the rules, laws studied so far. We would get a simpler expression, then we would implement that expression. We would obtain a circuit which of course would be very simple as compared to the original circuit. The functionality of both the circuits would of course be the same. So let us have a look. The expression is composed of 3 terms, the term A and B, the second term B or C ANDed with A, and the third term B or C ANDed with B. If you simplify this expression consisting of 3 terms, you have AB ORed with AB, ORed with AC, ORed with BB, ORed with BC. Now, some of these terms simplify. AB is common, so you just remove one of the terms. BB simplifies to B, so you end up with an expression AB ORed with AC, ORed with B, ORed with BC. This expression can be further simplified. B and the term BC, you have a common B, so you end up with B ANDed with 1 plus C. 1 plus C is equal to 1, so you end up with the term B. Now you have the expression AB ORed with AC, ORed with B. Now B is the common literal in the terms AB and B. So if you simplify these 2 terms, you end up with the literal B. So the expression is B ORed AC. Let us have a look at the circuits represented by the original expression having the 3 terms and the simplified expression having the 2 terms B ORed AC. The original circuit is made up of 3 AND gates and 2 OR gates. The OR gate used at the input has 2 inputs and the OR gate used at the output has 3 inputs. Altogether you require 5 gates. Let us now look at the simplified expression and the circuit resulting out of that simplified expression. Only 2 gates are required, an AND gate and an OR gate. So you have removed 3 gates. The circuit is simpler, less power is required, and perhaps it is faster than the original circuit. We have just looked at an example of simplification of Boolean expressions to implement simpler circuits. Again, this method would be used throughout the course. You would be writing expressions, you would be simplifying them to simplify and implement simpler circuits. So I would advise that you practice. You just write some expressions, you implement a circuit which represents that expression, and then you simplify the expression and then implement the circuit. आपने ये कंफर्म करना होगा कि दोनों सर्किट्स जो एक जैसा फंक्शन कर रहे हैं या काम कर रहे हैं. हाउ डू यू डू दैट? ऑफ कोर्स आप फंक्शन टेबल्स के थ्रू कर सकते हैं या वैल्यूज एक्सप्रेशन में दोनों एक्सप्रेशन में डाल के चेक कर सकते हैं उसमें. Now we have been writing expressions डिफरेंट टाइप की हमने एक्सप्रेशंस देखी. देयर आर टू स्टैंडर्ड वेज ऑफ राइटिंग एक्सप्रेशंस. वन इज द सम ऑफ प्रोडक्ट्स फॉर्म and the other is product of sum form. Before we look at the two ways of writing these expressions, let me describe what is the sum of product form. You have already been writing expressions in this form. Basically, you have product terms A, B, C. It's a product term. D, E bar. It's another product term. So, A, B, C plus D, E bar, it is sum of product terms. You have two product terms, you have summed them up. इस किस्म की जो एक्सप्रेशन है बेसिकली कैसे आप इम्प्लीमेंट करेंगे? बेसिकली यू वुड बी यूजिंग ए कॉम्बिनेशन ऑफ एंड गेट्स एंड एन और गेट. प्रोडक्ट टर्म्स कैसे आपको मिलेंगी? बाय यूजिंग एंड गेट्स. इन सारी टर्म्स को जब आपने जमा करना है, ऐड करना है, यू वुड यूज एन एंड गेट. लेट अस लुक एट द प्रोडक्ट ऑफ sum terms. Product of sum terms, as the name indicates, is sum terms which are ANDed together. So, let us consider the sum term A plus B. It is the sum term because you are implementing an OR operation between two variables. You have another sum term C or D. Now, if you AND these two terms together, that is A or B ANDed with C plus D, you get the sum of, rather the product of sum terms. Implement कैसे करेंगे? You would be using a combination of OR gates and AND gate. जो sum terms हैं वो आप implement करेंगे using OR gates. इन सारों का जो output है that would be connected to a single AND gate. Let us have a look at an example which shows the representation of different sum of product terms and product of sum terms. But before we do that, normally any expression can be easily converted into a sum of product term expression. Let us look at sum of products form first. There are three expressions. The first expression is A and B ORed with A, B, C. So, you have two product terms and they are ORed together. The second example is you have three product terms, the product term A, B, C, the second product term C, D, E, and the third product term B bar, C, D bar. Now, all these three product terms are implemented using three gates, three AND gates, and each of these three AND gates have three inputs. Sum of products is implemented by using a single OR gate having three inputs. The third example is A bar B. The second product term in this example is A bar B C bar, and the third term is A C. Again, a combination of AND gates and a single OR gate is used. You would require two AND gates having two inputs and a single AND gate having three inputs. You would of course require a single three input OR gate. Now, let us look at examples of product of sums form. Again, there are three expressions. The first expression has two sum terms which are multiplied together. So, the first term is A bar ORed with B. The second sum term is A ORed with B bar ORed with C. Now, both these two terms are ANDed together to give you the product of sums form. The second expression has three sum terms. The first sum term has A bar plus B bar plus C bar. The second sum term is C plus D bar plus E, and the third sum term is B bar plus C plus D. All these sum terms are ANDed together. Now, how many OR gates and AND gates are required? Well, there are three OR terms. So, three OR gates are required. What should be the inputs of these OR gates? Basically, in each sum term there are three variables. So, three input OR gates are required. Now, the final expression is product of these three sum terms. So, you need to have a three input AND gate to AND all the three sum terms. The last expression again has three sum terms. The first sum term is A plus B. the second sum term is A plus B bar plus C, and the third sum term is A bar plus C. Again, 3 OR gates are required. 2 OR gates have 2 inputs and a single OR gate has 3 inputs. The outputs of all these 3 gates are ANDed together by using a single 3 input AND gate. The diagram shows the implementation of the first sum of product expression. Again, 2 AND gates are used and a single OR gate is used. The second diagram shows the implementation of the product of sum terms. 3 OR gates are used and the results or the outputs of these OR gates are ANDed together to give you the product of sum terms. Any general expression can be converted to the standard sum of product form. Let us consider the expression AB plus B ANDed with the sum of CD plus EF. So, you have a product term CD plus EF. This entire term is ANDed with B, and this entire term is added with the product term AB. Now, if you simplify this, you end up with AB plus BCD plus BEF. The original expression is not in the standard SOP form. The simplified version has been converted into the standard sum of product form. Let us consider the second example. You have 2 sum terms ANDed together. So, the first sum term is A plus B, the second sum term is B plus C plus D. Now, to convert this into the standard sum of products form, you simplify the expression. So, you end up with the terms AB ORed with AC ORed with AD plus B plus BC plus BD. If you simplify this expression, removing the common terms, you end up with AC plus AD plus B, which is the standard sum of products form. The third expression is A plus B bar ORed with C whole bar. Now, this is not a standard sum of products form. Now, this has to be simplified. So, you end up with A plus B double bar ANDed with C bar. Now, what did we say when you have double bars over an expression? Basically, both the bars are removed. So, in this particular case, A plus B double bar is simplified to A plus B and C bar remains as it is. Now, if you simplify the expression, you end up with A C bar plus B C bar. So, you have converted the original general expression into sum of products form. Today, we have looked at Boolean algebra. We have simplified Boolean expressions using some rules which we have studied. We have also looked at simplifying circuits using Boolean expressions. We will continue with these Boolean expressions in the next lecture. Hope to see you again. Khuda Hafiz. Assalamu alaikum.